I'll wait for a couple of minutes and let people join, and then I will start. Okay, I think we can start. I hope I am audible to you and my screen is visible. I'm in the screen share mode. Can anyone please confirm? You can write in the chat box. So if I go to presentation mode once, then it is very difficult to check the messages. So I want to confirm if I'm audible and you can see my screen. Okay, thank you. So let's start. So good afternoon all. Welcome to the live session for the course Sensor Technologies, Physics, Fabrication and Circuits. This is week 4. Like always, let me start the session by introducing myself. I am Ananya, a PhD scholar in the Department of Electrical Engineering, IIT Kanpur. My specialization is microelectronics and VLSI, and I will be the TA for this session. So I'm conducting these sessions on Tuesdays around 6 to 8. So this is a problem solving session, but before starting the sessions and before going to the problems, I will briefly discuss the topics those were covered in this week, and then we can go to the problems. So the idea for these sessions are that we will solve, the TAs will solve few questions. Those will be helpful for your assignment problems so that you can solve your assignment. If you have any doubt in between, you can ask. I will try to answer your questions in the session itself, and if I cannot answer something, I'm not sure about something, then I will note it down and we'll discuss at the end, maybe in the upcoming sessions, or at the end before the exam we can have a doubt clearing session. So let's start the session. First, the topics those were covered in this week. So first topic was thermal sensors. So thermal sensors, this topic was covered, one part of it was covered in the last week in week 3, and in this week also one lecture was there on thermal sensors. I hope that you have already gone through the lecture videos and lecture notes, so I will only give a brief introduction about the topics. So thermal sensors are used to sense temperature, and based on the type interaction between the sensing element and the environment for which we are measuring the temperature, the sensors can be classified into contact and non-contact type sensors. So what happens in contact type sensors? The sensing element, that is these film, maybe a thin film or the metal or semiconductor that is being used as a temperature sensor, that will be in directly contact with the environment, outside environment. And in case of non-contact sensor, the sensing element will not be in direct contact with the environment. It will be encapsulated using some material, and it interacts with the environment with a certain window through which the temperature, like the heat energy, can flow. Okay. So these sensors can be classified as contact and non-contact sensor. And in contact sensors, the sensing element The sensing element can be a material like metal, it can be a thin film of semiconductor, anything. The sensing element is in contact with the environment. In case of non-contact sensor, the sensing element is isolated. And interact with the environment through a window. This is one way to classify thermal sensors. There are other ways also. So there are different types of sensing mechanism and different types of material uh, that can be used in thermal sensors. So most of the sensors, the sensing mechanism is where we utilize the property of change in resistance of a material with respect to temperature. So those sensors are known as thermoresistive sensors. There is something also. Uh, if you don't have any question, maybe you can mute yourself. Please mute yourself. I have turned I have turned off the like option for unmuting yourself. I will try. Okay, I think she has left. Okay, let's go back to the discussion. So most thermal sensors are of resistive type, and those are known as thermoresistive sensors. These are known as thermoresistive sensors. Why we use these sensors? Because resistance is a parameter, like it is an electrical parameter, we can measure it very easily, and we can design a circuit to interpret the like the resistance value. Because it is an electrical signal, we can interpret it very easily, and we can make like a readable sensor with some readable output, like in form of some readable output. Maybe in like using a display, we can make a system very easily. Say if the resistance value is in this range, then it is like a safe zone, maybe for some industrial application. If the resistance is high, the temperature is also high, it is not safe for the system in some, for some say industry application. So Resistive type sensors are very easy to implement and interpret and to make a system out of it. Okay, and what happens in resistive type sensors? The resistance of the sensing element is a function of temperature. Is a function of temperature. I mentioned in one class that the resistance change we can measure using a Weston bridge circuit. If there is any change in resistance, that will give rise to a change in voltage in case of a Weston bridge circuit, and that can be interpreted very easily with an electronic system. Now there are different types of thermoresistive sensors based on the material used. So there are different types of thermoresistive sensors. What are those? First one is RTD, resistance temperature detectors. Then PN junctions can also be used as a temperature sensor. Okay. And thermistors, these are very common. And there can be other types of temperature sensors also that utilizes the change in resistance due to change in temperature. Okay. Now these sensors can have positive or negative temperature coefficient. Okay, positive temperature coefficient or negative temperature coefficient, and whether the sensor is positive sensor has a positive temperature coefficient or negative temperature coefficient, that depends on the sensing element or the sensing material that is being used in the sensor. So certain material shows a positive temperature coefficient and certain material shows negative temperature coefficient. That means as the temperature increases, resistance decreases. We know that in case of metal, as the temperature increases, resistance increases, the metal heats up, and in case of semiconductor, as the temperature increases, the resistance decreases. So based on the material, sensors can be of different type, and based on the material, the working temperature range of the sensors will be different. For example, we may not be able to use a material that cannot sustain 1000 degrees Celsius. Say for some industrial application we need a temperature sensor that can go up to as high as 1000 degrees Celsius. Some material may not withstand that temperature. We know that in case of say polymer kind of material, some flexible material that we discussed in case of flexible sensors, I think in week 1, that certain substrates, certain material cannot withstand very high temperature, especially flexible substrates, most of the flexible substrates. So those are not suitable for high temperature applications. And what should be the mechanism, sensing mechanism, and what should be the sensing element, that depends on the application that we are targeting. So this is one topic that was covered in the first week, in this week, and the next topic was chemical sensors. So as the name suggests, it is used to detect some chemical reaction or the products due to some chemical reaction. Again, there are ways to classify these sensors. One classification is based on how the sensor output, how we get the sensor output. If we get the sensor output in form of some physical signal, change in some physical parameter of the sensing element, then the sensors are known as physically reactive sensors. And say due to the chemical reactions, some electrical property of the sensor is changing, then we call it as a chemically reactive sensor. This is one way to classify the chemical sensors. Can be classified as physically reactive sensors, say due to the chemical reaction, some physical property, stress, strain, or something like that of the sensing element changes, then it is a physically reactive sensor. Or it can be a chemically reactive sensor where the electrical property of the sensing element changes. Now another type of classification is those can be classified as direct sensor or indirect sensor. So what are direct sensors and indirect sensor? We know that in most of the sensors are of electrical type. So in direct sensor, we directly get output as an electrical signal. And in case of indirect sensor, the sensor output is converted to electrical signal using a transducer, using some external circuit. So it gives electrical signal as output. With the help of a transducer. I am trying to give you a summary of the topics dose vocabulary, okay, so that you can recall, and that will be helpful in problems. Now another way to classify chemical sensors that is based on the material or the sensing mechanism that is being used. So chemical sensors can be of different types based on the configuration or the sensing mechanism. One example that was discussed in the lecture videos is MOS type sensor, MOS sensors. Now this MOS is not metal oxide semiconductor. We are familiar in electronics courses. So this MOS is metal oxide semiconductors like zinc oxide, tin oxide, those materials. Those materials so react when it is placed like an outside environment, oxygen in the environment gets absorbed at the surface, and that will give rise to a certain surface potential. And if some chemical reaction happens on it in the vicinity, the surface potential will change, and based on the change in surface potential, the resistance of the material or the change in the surface potential will give indication about the chemical reaction that is happening, and the concentration of the target material that is being produced or that is nearby. Okay, so these metal oxide semiconductors based sensors are of mostly used in gas sensors application, where based on the reducing or oxidizing gas, the resistance of the material, the sensing film will change. Okay, so these are not these are metal oxide semiconductor based sensors. For example, ZNO or SNO2 based. One example of SNO2 based sensor that was I discussed in week 2, I think, where I showed one data sheet of a gas sensor where metal oxides are used as a sensing element. Another type of chemical sensor is PET type sensor, field effect transistor type sensor. You know what is a field effect transistors. We all are familiar with MOSFET, metal oxide semiconductors, and in field effect transistors, say in MOSFET, the current between the source and drain depends on the gate potential, and due to the chemical reaction, if the gate potential changes, the current between the source and drain will also change, and we can correlate the change in the current with the chemical reaction or the reactants, concentration of the reactants, and that's how we can actually sense and determine the concentration of the reactants. Okay, most common type of FET sensor which are used as a chemical sensor is FET. Okay, ion sensitive field effect transistor. Okay. Where the gate potential is changed based on the specific ion that we want to detect. This is very important. As we discussed earlier, selectivity is one of the main characteristics of a sensor. We want the sensor output to be changed because of the target analyte, not due to some other material, other chemical. So in ISFET, due to the concentration of that particular ion that we want to detect, the gate potential changes, and that gives rise to the output, that is the change in the source drain current, and that we can detect. So these are very specific to the target ion. So this is a brief introduction about the chemical sensors. Now the third topic that was covered is electrochemical sensors. Now, as the name suggests, it has two terms, electro and chemical. That means some chemical reaction is happening, that is that change, the chemical reaction is determined due to the change in some electrical properties. So now what are the electrical properties that can be changed due to some chemical reactions? Based on that, the electrochemical sensors are classified into three categories: potentiometric sensor, amperometric sensor, and conductometric sensor. Another category is impedometric sensor also, but that broadly the voltage, current, and the conductivity is like the opposite of resistivity. So basically these three properties can be changed in a system due to some chemical reactions, and based on what property is being changed, based on that electrochemical sensors can be classified into mainly three categories. So first one is potentiometric sensor. Second is amperometric sensor, and third one is conductometer. What happens in, as the name suggests, what happens in potentiometric sensor? So the voltage in the system changes due to the target material, or based on the concentration of the target analyte, the voltage will change. In potentiometric sensor, voltage in the system is a function of analyte concentration, and in case of amperometric sensor, current is a function of analyte concentration, and in case of conductometric sensor, conductivity is a function of analyte concentration. There are different ways to how we can realize these electrochemical sensors. Those were discussed in the lecture videos. I will not go through those again, but basically you can remember that here the electrical property changes due to chemical reactions. Next topic, or the last topic that was covered, is impedance spectroscopy. This is also one way of chemical sensing, used in chemical sensing. Now here impedance is a function of whatever the chemical reaction is happening. The main chemical reactions, those are actually we sense, are mainly redox reactions. Redox means oxidation and reduction reaction happening at the same time, at maybe at different electrodes. Here the concentration of the oxidant or reduced element, that depends on three factors. Okay, so there are three factors. When we want to design the sensor with model the sensor with some electrical circuit in a electrical circuit modeling, how we actually model the reaction of the system to an electrical circuit. We determine the parameters which are the factors which are affecting the the response of the sensor, and we try to fit with some electrical parameters, say resistance or capacitance. So what are these three factors or three things we need to consider while modeling the impedance sensor? First one is the mass transport by diffusion. So there are three phenomena. diffusion of oxidants to electrolyte. Okay. And another phenomena that is happening, actually the charge transfer reaction, that is basically the chemical reaction that is happening at the electrode. And third one is the mass transport. From electrode surface to bulk. Now the overall impedance is governed by these three factors, and the overall impedance of the system, or the overall impedance of the working electrode, is given by this formula. This is RCT plus, I am directly writing it from the lecture notes, by sigma by J over omega. So this resistance comes from this charge transfer reaction. Okay. If the reaction is happening fast, then this will be okay, so I'm not going to comment on that. So this comes from the charge transfer. This part we denote it using an electrical notation as RCT. And these two terms comes due to mass transport. Okay. How we can arrive at this impedance expression, that you can refer to the lecture notes. Okay. Now we can measure the impedance of a system, of an electrode system, using an AC signal, and based on the frequency of the AC signal, which phenomena is dominant, whether the diffusion phenomena, diffusion of reactants from electrolyte to electrode, or electrode to electrolyte, that is dominant, or actually the charge transfer reaction is dominant, the reaction kinetics is dominant. That will depend on the applied AC signal. Now if the frequency of the AC signal is high, at higher frequencies, RCT is dominant. That means we are in a kinetics limited regime, and at low frequency mass transport is dominant. Okay. So that means the effect of mass transport, actually that will affect the change in impedance more compared to the kinetics of the chemical reaction that is happening. Now this is briefly what the topics those were covered in this week. I will go to the next problems next. Is there any question? Okay, let me go to the questions then. First question is, which of the following statement is true? First statement is PTC, positive temperature coefficient type temperature sensor, where resistance decrease with increasing temperature. Next statement is NTC type is where resistance decrease with decreasing temperature. Third statement is RTDs are NTC type in nature. Fourth is thermistors can be either PTC or NTC. So which of the statement is true? You can write in the chat box. Do you have any answer? Only fourth is true. Yes. So here the correct answer is D. So in PTC type sensors, as the temperature increases, the resistance of the sensing element also increases. So this is PTC. In case of NTC, negative temperature coefficient, as the temperature increases, resistance decreases. The relation can be linear, exponential, but it will decrease in general. So first two statements are not correct. In PTC, resistance increases with increase in temperature, and in NTC, resistance decreases with increase in temperature. Okay. Now RTDs are NTC type in nature. RTDs can be NTC or PTC type. So what happens in RTDs? So these are resistance temperature detectors. Here the resistance depends on the temperature, and the resistance of the material is correlated, and RTDs are typically made using pure metal. Typically made using pure metal. Okay. What is the most common material that is used? It is platinum. This is the most commonly used. Another material, though another metals those are used as nickel or copper, but platinum is most commonly used, and they have positive temperature coefficient. We know that in case of metal, the resistance actually increases with temperature. The metal gets heat up, resistance increases. So in RTDs, mostly those are PTC type, because generally made using pure metals. Now in case of thermistors, are thermal resistors. Depending on the material that is being used in thermistors, it can be of PTC type or can be of NTC type. Okay. So these are mainly of NTC type, made using semiconducting material, where the temperature, as the temperature increases, resistance decreases. PTC type thermistors are used in circuits as a protective, like self-heating element. Okay. So as in PTC type thermistors, what happen, as the temperature increases, resistance becomes very high, so it limits the current. It can be used like a fuse. You know what a fuse does in an electrical circuits. So positive temperature coefficient type thermistors are mainly used as a reusable fuse in case of an electrical circuits, whilst most of the thermistors which are used as temperature sensors are NTC type. So thermistors can be either PTC and NTC type. I will write it down. PTC thermistors are used in series in an electronic circuit. As the resettable fuse. Because the resistance increases, so it acts like a self-regulating heating element. I hope there is no question, and we can move to the next question. Second question is, a thermistor has a resistance of 1 kilo ohm at 298 Kelvin temperature. And it has 465 ohm at 316 Kelvin temperature. The temperature sensitivity So what is temperature sensitivity? It is given in the question. 1 by r dr by dt, okay, where r is the resistance, of this thermistor at 316 Kelvin is. The options are A minus 0.040, B is minus 4, C is minus 0.4, D is minus 44. So what will be the answer for this question? We have to calculate temperature sensitivity of the sensor. The expression is given. How the sensitivity is defined here: 1 by r dr by dt. So this is T. And we have to calculate the sensitivity at 316 Kelvin. This is not like a linear relation, y equal to mx plus c. So the sensitivity at what point we have to calculate, that is given in the question. And as you can see, the sensitivity values are in negative. All the options are given as negative. So this is a NTC type thermistor. So I hope the question is clear. I'll give you some time to think about it, and if I don't get any answer, I will go to the solutions. You can use the expression for output of a sensor that was discussed in the first lecture for this week, thermal sensor. The expression was given as S equal to S naught exponential beta m by beta m into 1 by t minus 1 by t naught. Similar expression I have discussed in the first lecture also in week 1. The relation between resistance and temperature of a thermistor. You can use the expression. There are few unknowns, but we have few known parameter in here. For us, the output is resistance and the input is temperature. The input output values are given at two different points, at 298 Kelvin input and at 316 Kelvin input. At those temperature, what is the output of the sensor is given, and using the expression we can find the unknowns and find the sensitivity. I'm not getting any answer. Let me solve this. So for thermistor, the input output relation is resistance of the thermistor at a temperature T is given as R naught exponential beta 1 by T minus 1 by T naught. Okay, here RT is the resistance of the thermistor at temperature T. R naught is some reference temperature, a reference resistance. For temperature T naught. That is known to us for the sensor. T naught is the reference temperature and beta is material characteristics temperature that depends on the property of the material. Now this is similar, the similar expression was given in the lecture note. I am just using these notations because it is a thermal sensor, it is a thermistor where the resistance depends on the temperature. So in the lecture note the expression was given as S, the sensor output is equal to S naught exponential beta m 1 by T minus 1 by T naught. This is essentially the same relation. Okay. Now what are the information those are given to us? So it is given that at 298 Kelvin the resistance is 1 kilo ohm. Just give me a minute. So at 298 Kelvin resistance is 1 kilo ohm means 1000 ohm. I am writing everything in ohm, and let's keep this part as same. R naught exponential beta, let me take this out, minus beta by T naught and exponential beta by T, and our T is 298 Kelvin. Okay, so this is our first expression. Another information that is given to us, the resistance at 316 Kelvin is 465 ohm. So at 316 Kelvin it is 465 ohm. Let's keep this part as same because we can cancel it later. R naught exponential minus beta by T naught exponential beta by 316. So R naught is our constant, that is the resistance at temperature T naught, that is also constant, and beta is already a constant, material specific. Now let's do 1 divided by 2. What we will get, 1000 by 465 is equal to, this part will be cancelled out, R naught exponential minus beta by T naught. We will have exponential beta by 298 minus beta by 316. I hope everybody is okay with this. Next, take logarithm on both sides. This will be ln of 1000 by 465 is equal to beta by 298 minus beta by 316. So beta is our unknown here, so this will be 298 into 316 minus 298 into beta is equal to ln of 1000 by 465. I hope that you are also doing along with me, and you can tell me what is the value of beta. This value we need to calculate our sensitivity. Ln of 1000 divided by 465 is 0.7657. This is into 298 into 316 divided by 316 minus 298. So the value is 4005.89. What will be the unit of beta? I hope that you also get the number here. What will be the unit of beta? Beta is material characteristics temperature. So even if you do the dimension analysis here, beta should have a unit of Kelvin, okay, so that it gets cancelled and we finally get whatever the unit of S0, because S0 and S or R0 and RT should have the same unit, okay. So this unit is Kelvin. Now we get beta, the unknown parameter. Now we can calculate 1 by R dr by dt. So that is what we need to calculate, 1 by R dr by dt. Let's calculate that. 1 by R dr by dt is 1 by R0. So this is basically RT. We are doing it at a particular temperature. 1 by RT exponential beta 1 by T minus 1 by T0. Okay, so this is 1 by R. dr by dt is differentiation of this expression with respect to T. So that will be R0 exponential e to the power minus beta by T0. This is constant. Then we have to differentiate exponential beta by T part. Okay, so that will be exponential beta by T, and we will differentiate again beta by T, so that will be minus beta by T square. Okay, we are differentiating it with respect to T. I think this is clear to everyone. Okay, now these part will be cancelled. Finally we will get the expression as beta by T square. Okay, now we have to calculate the sensitivity at 316 Kelvin. So we'll put the beta value minus 4005.89 divided by 316 square. The unit will be Kelvin inverse. Okay, so what will be the value of our sensitivity at 316 Kelvin? 4005.89 divided by 316 square. This is minus 0.040 Kelvin inverse. This is our output answer. So our answer is A minus 0.040. Okay. I hope the solution is clear to you. Is there any doubt? And I hope that you are also doing the solution along with me. If there is no question, let's go to the next question. I will write the question first. Which of the following is not true about thermistor and RTDs? First statement is thermistors are more accurate and cheaper than RTDs. Second statement is thermistors have faster response time than RTDs. Third statement is thermistors can measure temperature over a wide range than RTDs. All are temperature sensors, RTDs and thermistors, but the properties are quite different. And why we need to know that? These because say we want to use those as a thermal sensor for a particular application, and which one is more suitable for our application, that we have to determine based on the properties. Third statement is thermistors are commonly made with ceramic or polymer material, while RTDs are made of pure metals. So which one is not true? Please try to answer in the give the answer in the chat box. Thermistors are more accurate and cheaper than RTDs. Thermistors have faster response time than RTDs. Option D. Option D is, so the question is, which of the following is not true about thermistor and RTDs? Option D is actually true. It is not the correct answer, because thermistors are mainly made with ceramic or polymer material, but RTDs are made of pure metals. In the last one of the questions I have mentioned that RTDs are made using platinum, nickel or copper, while platinum is the most commonly used material, and that is why RTDs are mainly PTC type, positive temperature coefficient type, where the resistance actually increases as the temperature increases, while thermistors can be of NTC and PTC type depending on the sensing material, property of the sensing material. Okay, those can be of semiconductors like ceramic, insulating type material, where the resistance change depends on the material properties. So I will let me give you a comparison between thermistors and RTDs, so that will be useful for you. I hope so. So comparison in terms of temperature range, because in one of the option it is given thermistors can measure temperature over a wide range of RTDs. So let's see. In case of for temperature range, if you compare thermistors and RTDs with respect to the working temperature range, then thermistors are typically used for lower temperatures, because the material that those are generally used in thermistors are as given in the here, like can be ceramic or polymer material, or it can be different combination, like the composition of the material can be different. Those materials normally cannot sustain higher temperature compared to metals. We know that metals can sustain very high temperature, that's stable at high temperature. So thermistors are typically used for lower temperature, generally below 250 or 300 degrees Celsius, because if it is made of polymer, then it will not sustain at high temperature, while RTDs are it can be used at a very high temperature, generally used at say 600 degrees Celsius or so. Okay, so temperature range wise, thermistors are typically used for temperatures below 250 degrees Celsius. I'm not giving you any reference for this. This is not like exactly it is always used below 250 degrees Celsius. The point I am making here is that thermistors are generally used for low temperature applications, while RTDs are used mainly for high temperature applications, because those are made up of pure metal. Next comparison is in terms of accuracy. Thermistors are generally more accurate compared to RTDs. Okay, the sensing element or the composition of the sensing element is made in such a way that it is more accurate, gives more better results compared to RTDs at mainly at low temperature. At high temperature, anyway we cannot use thermistors. Okay. Next comparison is in terms of cost. Say, so thermistors are easily available. Those are generally have low cost compared to RTDs, which are made up of pure metal. Okay, RTDs are of pure metal, so those have higher cost compared to thermistors. You know, the most commonly used material is platinum, and that is expensive. And application wise, as I mentioned earlier, application of a sensor depends on the properties of the sensor. So as I mentioned here, the RTDs can be used for higher temperature, so those are used in industrial applications where the high temperature processes are involved. Say we want to measure temperature as high as 1000 degrees Celsius, 600 degrees Celsius, 700 degrees Celsius. In that case, RTDs are used. And in case of say home appliances in household environment, we typically we can use thermistors because the temperature does not reach that high. Okay. In medical devices also, where the accuracy is important. I hope that you can understand my writing. Okay. So these are the comparison between thermistors and RTDs. So I have noted down so that you can quickly refer to it whenever you need. So let's go through these statements. Thermistors are more accurate and cheaper than RTDs, so this is true. Okay, thermistors have faster response time than RTDs. This is also typically true. Now, thermistors can measure temperature over a wide range compared to RTDs. So this is not true, this is false. We know that at higher temperature, thermistors cannot be used, and thermistors are commonly made with ceramic or polymer material, while RTDs are made of pure metal. So this is true. So our answer is C. Thermistors can measure temperature over a wide range compared to RTDs. I hope it is clear, and we can move to the next question. Which one is not true? Yeah, I mentioned that like our thermistors cannot be used for higher temperature applications, so the working temperature range is limited for thermistors, while RTDs can be used at higher temperature because of the material that is used in RTDs. Next question is, the following gas selective membrane is used if membrane is ion penetrable. This was mentioned in the lecture note. Try to recall and tell me the answer. MEMFET. B is SURFET. C is NFET. D is ISFET. So FET, field effect transistors, can be used as a chemical sensor. The ion that is associated with the chemical reaction, that concentration can be used to change the gate terminal, gate potential, and that will change the drain current, source, the current between the source and drain, and we can correlate the drain current, change in drain current, along with the change in ion concentration that is related to gate potential change. So based on the configuration, like based on the type of the ion and what we want to actually sense, the FET configuration are a bit different, and those are known as MEMFET, SURFET, NFET or ISFET. In case of the ion of our interest, the ion that we want to detect, the concentration of the ion that we want to detect, if that is penetrable through a membrane, gas, say ion selective membrane, then what is the type FET configuration we use? That is the question here. So what is the answer? You can read about this different type of FET configuration which are used as a chemical sensor by yourself. Only the these topics were very briefly discussed in the lecture note, but if chemical sensing is of your interest and specifically using a FET type configuration, say using a field effect transistor, you want to do chemical sensing. If you are working on this area, then you can read more about it. I'm also not very familiar with these techniques other than maybe ISFET, because that is the most common configuration that is used, and I'm a bit familiar with ISFET, not much. I don't know much about the other types. So I have studied also for this session, like how FET is used as a chemical sensor. So what is the answer? So the answer here is MEMFET. If the membrane is not ion penetrable, then it is known as surfeit. And what is NFET? If there is an enzyme coating at the membrane, like at the gate terminal, and that is sensitive to particular analyte, so that the gate potential changes because of only that particular analyte, that particular target analyte, that kind of configuration is known as NFET. You know that enzymatic reactions, those are very specific, like a particular chemical will react with a particular chemical, not with others. So if we want to ensure that our sensor is detecting only the target analyte, then an enzyme coating is used, that is known as NFET. And ISFET is also similar. ISFET is ion selective FET, where the membrane at the gate coating is actually sensitive to it is selective to a particular ion. Okay, the gate potential changes based on the change in the concentration of a particular ion, so that is selective. Okay, so this is ISFET. So you can read more about it, like how a FET is used as a chemical sensor. Let me write the next question. Which of the following is not correct? First option is adsorption is surface phenomenon. Second statement is adsorption is exothermic in nature. Third statement is absorption. This is about absorption. exothermic, in nature. D is absorption is bulk phenomenon. So which one of these is not correct? Which one of these is false? I think you can answer this. This was discussed. The difference between adsorption and absorption. Even though it sounds similar, but both the processes are different, and based on those differences, which one of the following statements are not correct? No answer. So when we studied absorption and adsorption, we studied it in chemical sensors. I think right after MOS type sensor, metal oxide semiconductor type sensor. The working mechanism of MOS type sensors are based on adsorption of chemical species on the sensing element, on the sensing film. So what is adsorption? Suppose this is our sensing element or sensing film. In adsorption, in this process, materials get absorbed at the surface. So these are at the surface. So here the first statement, adsorption is a surface phenomenon. It's a through statement. It only happens at the surface, and it is generally a exothermic reaction. Like the process is exothermic. Okay. And what is absorption? In absorption, what happens? If this is our sensing element, the chemical species will go inside of this material. This is basically the absorption process. It is a bulk phenomenon. And this absorption process, it has less dependency on temperature and generally endothermic. So absorption is exothermic in nature. This is also true. Absorption is exothermic in nature. This is false. Typically endothermic. Absorption is a bulk phenomenon. This is also true. So our answer is C. So this statement is not true. So as I give this kind of theoretical question, I hope that I get the answer. Like, if it is a numerical question, it is not easy to solve immediately, that I understand, but in case of this multiple choice type question, I expect that I will get answers in the chat box. And I hope that you know what is exothermic and endothermic reaction. So in exothermic reaction, so in those reactions generally heat is released, whereas in endothermic reaction heat is required, like the concept of enthalpy. So I will not go into details of it, just briefly, in exothermic reactions heat is released. Let's go to the next question. Which of the following is true for chemical sensor? First statement is, in physically reactive sensors, this is S. Reaction changes chemical property of active material. Statement B is, in chemically reactive sensor, reaction changes physical property of active material. Option C is, sensing changes in optical strength, basically the output of a sensor is, if optical, which gets converted to electrical signal. This is an example of indirect sensing. Which of these statements for chemical sensors is true? I have already discussed in this session itself uh, how we can classify the chemical sensors as physically reactive and chemically reactive, as well as direct and indirect sensors. So I hope that you can answer this question. So I am waiting for the answers in the chat box, so that I'm actually sure that there are people in the meeting and you are actually following what I am saying, and you are also like solving the questions along with me. So what is the answer? Which statement is true among these options A, B and C? A and C. Okay. So what happens in case of chemical sensors? If we are classifying it as physically reactive or chemically reactive, so both these type of sensors sense some chemical reaction, but the chemical reaction that is happening may change some physical property or chemical property, or say electrical property of the sensing element. Now this classification is based on what property of the sensing element is being changed. Okay, so the option A is in physically reactive sensors, reaction changes chemical property of the active material. That is not true. In physically reactive sensors, the reaction changes some physical property of the some physical property of the sensing element. Okay. The physical property can be like the change in a physical property can be the, maybe say due to the chemical reaction, there is a bend in the sensing element, like, okay, so there is some stress, some strain, due to which the shape of the sensing element is being changed. So those type of sensors are known as physically reactive sensors, whereas in case of chemically reactive sensors, change in the electrical properties of the sensor, say the conductivity of the sensing element changes. Okay. Say due to change in ion concentration, the conductivity of the sensing element changes, or the sensing film may be changed. Okay. So those are chemically reactive sensors. So the examples we have discussed, mostly those are chemically reactive sensors. Now other type of classification is direct and indirect sensing, right? Here the output is electrical signal, and In case of indirect sensor, output is converted to electrical signal with the help of a transistor. So the actual output of the sensor is not an electrical signal. It can be converted into electrical signal using some circuitry. What a transducer do? It changes one form of energy to other form of energy. Whatever the form of the output of the sensor, it will convert it to electrical signal, electrical output. Okay. So here the answer is, which statement is true? First statement is not true. The reaction changes chemical in a physically reactive sensor. Reaction changes the physical property of the active element. So this is false. In chemically reactive sensors, reaction changes chemical property of the active element. It is very clear from the name itself. And third statement is sensing changes in the optical strength, which gets converted to electrical signal. This is an example of indirect sensing, so this is correct. Here the optical signal is converted to electrical signal. Okay, so here the answer is C. We have few more minutes. Let's quickly go through one more question. The question is, the displacement sensitivity of a capacitive type sensor is given by the expressions are given. First is minus epsilon naught A by x square. Option B is minus epsilon naught A by x square. I think this is cube. This is cube, okay. Option C is minus epsilon naught A by x to the power 4. Option D is minus epsilon naught A by x. So we have to calculate the displacement sensitivity of a capacitive type sensor. We have to calculate the sensitivity where we are using displacement sensitivity, means here the displacement, that is the distance between the plate, is being changed, and that is what we are measuring. So our sensitivity will be change in capacitance due to change in displacement. Okay, so this question is on parallel plate configuration of a capacitor. So this is a parallel plate configuration, right? We apply a voltage here, and this is ground. This is the distance. As per the notations given in the options, I am taking it as x. Okay, this is our input. X is the displacement. This is our input for the sensor. This is being changed due to some phenomena, that is what we want to measure. And C is the capacitance between these parallel plates. This is our output, that is what we are measuring. Okay, so because of some phenomena, displacement, distance between these two parallel plates are being changed, and our that is what is our input, displacement is our input, and capacitance is our output. So you know that the capacitance for parallel plate configuration is epsilon naught A by X. Epsilon naught A by the distance between the two parallel plates, that is being denoted as X here. Okay. So this is the capacitance formula, and what will be our sensitivity? Sensitivity will be dC by dx. So sensitivity is delta output, change in output due to change in input. Okay, so this is dC by dt. We will differentiate the expression of capacitance with respect to x. That will give us sensitivity. Okay, so this is epsilon naught A is constant, and 1 by x, the differentiation will be 1 by x square minus 1 by x square. Okay, so this is our sensitivity. So what is the answer? Answer is what is the expression? Okay, answer is B, minus epsilon naught A by x square. Okay. This is the sensitivity if our input is displacement or the distance between the capacitors. If our input is say A, then the sensitivity will be different, even though it is the same configuration, parallel plate capacitor. If our input is say epsilon naught, that is the permittivity of the dielectric medium in between the plates, and due to some change in the system, the permittivity is being changed, so that is our input, then the expression for sensitivity will be different. So here you have to see the sensitivity, what with respect to what we want to calculate. It is the displacement sensitivity. Okay. So I hope this question is clear. If there is any doubt related to today's session or previous sessions also, you can ask. We have couple of minutes. If you have any question, you can ask. Option B. Here we can have one doubt clearing session or summary session at the end before the exam. We can have that. Yeah. Okay. So, any more question with question number 4? So week 3, you are asking in assignment. See, I am not supposed to discuss what is the due date for it. Due date is okay, so the due date is already over, so okay. Question number 4. Okay, so this is a interdigited kind of arrangement. So there are 10 electrodes, right? Between these two electrodes there will be one capacitance. Okay, so between 1 and 2 there will be one capacitance, between 3 and 4 there will be one capacitance. So you can see there are 10 electrodes and there will be 1, 2, 3 okay, I'm not in a screen share mode. Let me share. So this is the fourth question. You can see my screen. So there are 10 electrodes. So between first electrode and the second electrode there will be one capacitance. So in total there will be 1 2 3 4 5 6 7 8 9 capacitance. Okay, so if there are 10 electrodes, then there will be n minus 1, that is 9 capacitance between these electrodes. Now for one of the capacitance, say between 1 and 2 electrode, the you can calculate the capacitance by using a formula for parallel plate capacitor. C is equal to epsilon A by D. Okay, distance is given, D is given 50 micron, and length is given. Okay, and area is given. So you can calculate epsilon A by D, right? So since this value is not given, like the epsilon value is not given, take it as epsilon naught, permittivity of the free space. Okay, so you can calculate capacitance between 1 and 2 electrodes. Then you can multiply n minus 1, that is 9 for this case, and then you can get the overall capacitance. I have not calculated it, so you can calculate it, right? The formula will be, just writing it. A is given, D is given, N is 10, you know, these two are given, and epsilon naught, this will be permittivity of free space. Okay, then you can calculate it, you will get the answer. Okay, try it by yourself, but this is the way to solve this question. Okay, is it clear? Okay, yeah. If you don't, if you cannot get the answer, I will do it in the next class. It's almost the time is over. So, but this is the formula. You will get the answer. This is the way to solve this question. Okay. Thank you, everyone. Thank you for attending the session. I hope the session was useful, and let's meet in the next session.